So I start with sort of operational data. This is the data we're going to talk primarily about in this course. And I sort of frame it as a pyramid in the following way. At the end of the day, everything starts down here as, sensor data, right? Like something was measured in some sensor or in the factory. And some data stays there, right? Not everything is pulled out of the PLCs. So then what's the next level, which is again a subset of this. And I call this production cycle data, but this is data which you can link to a specific like cycle on a machine. This pick and place was making this panel right now, and here's everything we know about what it did. So it's one extra level of contextualization where, okay, I know at least which unit was in the machine when this data was collected, what it might be relevant for. And we can separate that into two parts. The process steps, these are like assembly processes or things that don't intrinsically have a test or an inspection pass or fail. You're sort of assuming it passed, or you don't know if it passed until something else tests it. Then you've got the ones like the SPI, AOI, AXI, your test machines, your functional testers, your ICTs, all the machines for which there's an intrinsic sort of pass fail that's associated with the result. So this data is, available in the equipment, oftentimes, and oftentimes you can harvest it out. But what I want to highlight here is, it's not the case that this data is sort of fully contextualized to the product that's being built. So for example, where you might know, take like a SDI, for example, or actually, let me take like a solder paste printer. Not all solder paste printers might scan the barcode of the unit that they're printing on and put that in with the data that's sending. So yeah, you know exactly that this data is associated with a PCB panel, when it was processed. But if you wanted to go look in your MES and say, okay, look at all of the product rep steps that it took to make, product start to finish, you wouldn't necessarily see this data in that level because that barcode link wasn't scanned. You don't have it, you have it in the MES, it was left down one layer below. So you've got this sort of next layer in the pyramid, which is what is the subset of the production cycle data that for whatever reason was decided to actually do the extra effort to contextualize it, put it into the MES, maybe link it to a production route, link it to a unit. And so you have this sort of like subset of data that might be in your MES system or might not be, but might be possible to fully link on demand if you want to, because the right identifiers and usually serial numbers are present. And then even on top of there, you might have one higher level of data, which is, based on all of this, what are the sort of non-conformances that were found in the unit? What are the repairs that were done? Some sort of like top level of human aided analysis or human aided understanding on top of that data. And what I want to emphasize is, in every factory, it's not the case that everything from sensors makes it to contextualize, because that required work for someone to put it together, to scan some barcode, maybe add another barcode reader, maybe do some integrations. So there's actually a lot that gets left behind these various stages. And that just is the nature of the situation. Typically, like this is the piece, the production cycle data. That's where I think a lot of the most interesting data lives. And to the extent that you can contextualize it, it's better, but oftentimes it's not. So sometimes you just live in this middle little well here. So this is sort of like the machine data piece here. And then it sort of lives in a context, right? Sort of like from the top down here, where you've got maybe your master data in the factory, what products do I have as my inventory, what orders am I trying to fulfill? You have the context of like the factory physical layout. What are my lines? What machines relate to each other? You have the product routing data. What are the steps required to build each of my products? What's optional versus required? What are the possible routes? And then you have your actual production plan that you're trying to achieve, in a given week. This would be like sort of your operational data that would be used to inform or understand, all of the data coming off your equipment. So then you have maybe supporting data. Or this one on the right. Maybe information on production resources. Okay, what tooling, maintenance histories on your equipment, maybe the calibration state of the equipment, information on people, certifications for certain operations or staffing levels for different shifts. And then also, your machine programs and recipes that, ultimately would be used in here, but maybe are stored and controlled, somewhere else. So you have all these sort of production resources here on the side. And then you also have a number of sort of reference documents. So you might have all of the SOPs in the factory, how processes should be performed, your trainings. You've got manuals or detailed information on all of the equipment. You've got information on the products you're trying to build. maybe design documentation from a PLM system or from the customer if you're an EMS factory building someone else's products. And you also have, all of the, call them human generated reports whenever something happened that was unexpected. Okay, maybe a downtime investigation, maybe an AD investigation report, maybe an FMEA analysis or a CAFA based on some previously found nonconformance or quality violation. So this is sort of the world of data that you have in the factory. I would say the data on this side is primarily documents written by people for people. This is structured data, but sort of slowly varying about the state of things in the factory. This is what's changing every single day, like every cycle. I get a new cycle data here. Maybe it's contextualized. Maybe it ultimately gets up and tells us something about the product that's being built. And then this is sort of the context in which I interpret this data. This is sort of all of the pieces of information, in a factory. And like this is the one that we're talking about primarily in this course. And then the subset that makes it here. And then we'll talk about the sensor data insofar as talking about the work that it takes to get it up level into production cycle data if it wasn't naturally built that way already by the equipment. So this is sort of at the world of data in your factory. And this is the one that we'll talk about systems to collect and harvest. Previously, I wouldn't have mentioned these other ones because it wasn't sort of clear how you would unify them together. Like, how would I take an equipment manual and use it with production data? Like a person could do that, but no system can do that. That's changed now, right? Like, you can feed an equipment manual into ChatGPT and ask it to summarize it for you or summarize it in the context of a problem. So it's sort of relevant now to talk about like these pieces as well, insofar as they inform how you might build, say, an agent that might analyze production cycle data for the purposes of answering a question or solving a problem. So then if you look now at this red box, then what do we find inside there? Okay, what is that particular data? And break it down into sort of 4 buckets. Performance data, process data, inspection or error code, inspection or test data, and then error and fault data. And what's inside each of those? So inside, the performance data is things like cycle times, how long does something take, what was the throughput, any shortages that were discovered, pick and place ran out of parts or couldn't pull from a feeder, so it stopped. In process data, these might be all of the sensor readings that were recorded, measurements made on the unit. The machine might automatically correct some small deviations. So, okay, what were those corrections? Those can also be an interesting source of understanding maintenance or calibration before it drifts too far and it can't correct it. And then maybe whatever details it has on the exact operations it was performing. On the error side, things like material issues or maintenance issues, programming issues, whatever the machine knows and the error code is capable of spitting out, that might tell you what's going wrong. And then, on the inspection results side, you have, at the end of the day, the top level, pass or fail. Then the one level down, okay, what's the categorized defect that was found? What did the machine understand? Maybe what did the human think it was? And then this is supported then by a number of measurements, often many more measurements than the ultimate pass or fail. And these measurements can be super valuable on their own, even for units that ultimately passed. So for example, an SPI machine might make 5,000 or 6,000 measurements or more on a large PCB, ultimately to find 0 defects and everything passed. But those 5,000 measurements, if you analyze them in the right way, could tell you a lot about the health of the solder paste stencil. For example, it could tell you I was starting to get a clog on one of the apertures. Hasn't been a problem yet, or maybe someone decided to set the bounds really wide on that process so everything passes. But still, you put the machine there for a reason. Might as well look at what it's doing and see if it can tell you something of value. So then just visually, what does this look like? You have machine performance data, things like cycle times. In process data, things like, this is a pick and place example, all of the attrition rate by nozzle or feeder, all the little mistakes that are automatically not fixed up, but the machine tries again and continues going. Things that might fly under the radar because the machine hasn't stopped, but could tell you important things about health or just prevent attrition or wasted money on parts. On the inspection data, things like passes and fails, defects, and then to the extent that you harvest them, also the underlying measurements that come supported by this. And then, on machine errors, this varies widely, but, this is an example on an ASM pick and place, for example, all the things that the machine knows. like what stopped, had fiducial problems, couldn't load a board or whatever. And one of the nice things about error codes is they sort of intrinsically have a built-in Pareto, even grouped by error code, and then look for common causes. Okay, so this is now all at the production cycle level. So what's the work required to contextualize it? Let's say I wanted to, link it all. So we're starting down here, the production cycle data. So I've got all of my data from each machine. It knows, okay, I've been a cycle. Here's everything I know. Usually the way this goes next is if the machine knows the serial number of either the panel or one of the units on there, it can then look up a work order. Based on the work order, find the product, and then based on the product, it can say, okay, this was step 1 to build that product, step 2, step 3, get that whole product route, which of course spans the entire factory, not just necessarily one factory line. And like this is the work that would be done to contextualize what the machine knows and put it in context of this particular unit. This was data on step 5, I got data on step 7. This then would be sort of like the final assembled data. This would be what that contextualized machine data block would be. If I go here, this one. But, it's usually not always the case that every intermediate machine knows the serial number of units it's processing. There's actually a step that was required, maybe an extra barcode scanner. There's a lot of technical work going into making this easier to do. So IPC has the Hermes standard. The Hermes standard, its primary goal in life is to allow scanning a barcode once and have it pass the barcode down to every single machine on the line. And the reason to do that, one of the reasons is so you actually can link all of the data together from that entire line and contextualize it without needing to say, like, am I going to put in a bunch of extra barcode scanners to be able to do that? But most factories have not fully implemented that. So it still is the case that there's a lot more data that the machine knows about what it did than what was able to make it into the contextualized layer and be reliably linked into the product lifecycle. And this of course varies strongly by the kind of manufacturing. In medical manufacturing or automotive, there might be much higher traceability requirements, which would have forced this higher level contextualized data. But even in those cases, it's usually the case that there's a lot more here that ultimately made it there. So why is this so interesting? Even before AI was interesting, and the interesting things have remained that have actually gotten even more interesting. So number one is, this data volumes are high, right? Machines collect this data on every single production cycle, both normal and abnormal, which is particularly nice because this highly standardized and repeatable method of collecting data on both normal and abnormal operations can allow it to be somewhat self-baselining, right? If you have a normal mass production scenario where maybe my yield is 99%, I get 99 passes for every one failure. It means I'm building up like a nice big picture of, okay, what does pass look like? And that can help analyze that data to understand, okay, what are subtle signs of not quite failure, but getting to failure? So what are the tails of that distribution look like on the pass side? That's one of the reasons why it's particularly interesting. And I like to highlight this with an example. So what I have here on the right is, I'll call it like a standard hourly performance tracking dashboard. Something you might find written on like a whiteboard on extra factory line. So this is time, 24 hours. And then up here is the number of units completed in that hour. So if I look at this, I can say it goes up, it goes down. And just to be clear, this is exactly one product, one line. There's no changeovers here, same product. So you would expect maybe just a flat overall line. And what you find instead is sometimes I make 100 things in an hour. Sometimes I make 60 things, but there's really nothing more I could say from that chart. Like, why is this the case? I just know that I've got some opportunity here to make this line run maybe at a slightly higher pace. If you look at the underlying data that came from the equipment, and this is now the bottleneck machine on the same line, what I'm showing here is the individual cycle time of that machine. So, and by cycle time here, I mean the time between two subsequent boards leaving that same machine. So basically a measure of how long it's taking for things to go through this line. And the first thing you can see is way more interesting and structured than this thing. This is the same data. This is just average, once an hour. And this is the underlying every single cycle. And if you look at this, You can identify, oh, I had some machine faults that just stopped the line for 5, 10, 15 minutes. I can analyze those and figure out what's going on if I want to get some cycle time back. You can see here periods of time where for 15, 20 minutes, the line is running. It didn't stop, but it was running about a third as fast as you know it's capable of running. And why do you know that? Because you see all of the actual sort of standard cycles of like how quickly the line should be moving when it's working correctly. So all of these things can be analyzed and inferred just by looking at the information on exactly how long did each individual cycle take to come off that line, each individual unit, knowing that they're the same product and doing the same operation, so it should be flat or not interesting. But in practice, there's a ton of variation. Um, and if you don't look at the sort of underlying data, you only look at the hourly graph, you really can't say why. But when you look at the underlying structure, now there's a lot of interesting things that you could analyze to figure out how you might make this line run faster. So then in the context of electronics manufacturing or S&T specifically inside there, there's a couple other examples that I like to give. So number one is tracking the origin of defects. I've got a defect at AOI, and the AOI machine only knows which component was defective, but it doesn't per se know, okay, which nozzle or feeder from the pick and place machine placed that component. So if you look only at the data from the AOI machine, you get a picture, you get a Pareto of defects, but you don't necessarily know the root cause, because usually it's going to be correlated with some physical thing either on the stencil or on the oven or on the printer, or sorry, on the pick and place. So if you take information from the pick and place, you put it together, and now you take all of the defects that you found at AOI and you annotate them with, okay, what nozzle was used for that exact placement, which is something that's known from the pick and places program. You could pull that off in a file and you could annotate it. You sort of see things like this, where, hey, I've got a problem with one of my nozzles, it's a little bit worn, or maybe I've got a problem with my camera, it's a little bit like off in its calibration. And you sort of identify, oh, actually, yeah, the accuracy of my placements, if I look at everything, it was maybe, plus or minus a millimeter, but actually that's just because of one bad nozzle. And now with that data linked together and annotated, collected on every single placement, I can say, well, if I go and fix up this one nozzle, I can take my repeatability down to say like 0.3 millimeters on this placement. And this is just something that requires putting data together from two machines and then looking at what you can now say, given what the pick and place knows and what the AOI knows. A similar example is, feeders. So if I look at aggregated data only, so I just look at maybe an overall daily attrition rate at pick and place. Well, this is the number of dropped or mispicked up components that were put into a reject bin, across my factory. Like overall, you're going to say like, okay, kind of goes up, kind of goes down. But if you were then break this down and track the individual attrition rates of every single feeder, then you of course find that what drove this was just a large anomaly on one feeder. This is sort of like looking at individuals versus the overall population. So by tracking this data individually, you're able to pull back much closer to the area of the factory. You don't know the root cause, so you don't know why this happened. You know exactly where to look. Of my 500 feeders, is this one. Everything else is fine. So these are sort of three examples of why collecting and storing this production cycle data gives you a much more rich data set to sort of answer some of these deeper questions than just sort of the overall like hourly or daily KPI, which is interesting to track from a performance point of view, like how am I doing? Am I getting better or worse? But doesn't really have the richness to then go one level deeper or two levels deeper and say, okay, why? Well, what might I do to make this KPI better or make a stock get bad? Okay, so I want to give one more example of what you can do with machine data. This one is not an electronics example. It's from actually a vaccine factory. It's more about in the batch manufacturing, but I give it because one, it shows some high value problems that you can solve with machine data, but two, it's the kind of thing that you can now start sort of automating investigations using some AI tools. So previously, like this was really hard to do, but possible. Now it's moderately hard to do And so it's applicable to a wider set of situations. So in this case, this is data on a series of valves in a chemical plant. And the valves, there's 5,000 of them. So there's all these reaction chambers. You've got like liquids mixing and to create this vaccine. There's a giant reactor. And these are all centrally controlled. So the value of the valve, open or closed. But the valves have no health sensor. You don't know when they're going to break. But they break on occasion. And the failure is only detected once it impacts the downstream product quality. So the question is, could you predict when a valve would fail? And this super high value is a vaccine plant. Downtime is very expensive. But with 5,000 valves, you'd have to take the plant offline to replace one of them. So there's a really high cost to also do proactive maintenance. You got to find that balance. So this is sort of what the data looks like. This is one valve. And you look at this as like 0 is fully closed, 100%, 80% is mostly open. This is over a period of number of months. There's a bunch of different batches of the same vaccine flowing through here. And if you sort of look at this, there's nothing obvious that you can tell. Kind of goes out, kind of goes down, unclear. There's a couple failures in here in the data, but it's not clear exactly where they might be or how you might predict them. So then, but you say like, well, actually, I know it's a factory. I know there's highly repetitive operations going in here. In fact, I also know, I know exactly when the same recipe is being run on this factory. So now what I'm doing is showing you 35 runs of the same vaccine recipe over a period of months. And this is, about, say, 400 seconds after the recipe starts. And okay, now I see some structure. I'm starting to see that darker colors are older runs, lighter colors are newer runs. It's still not clear, like if I could predict anything, but at least I'm starting to see some repeatability and some structure. And I do know these lines should be identical because it's the exact same recipe being run. I know it's repetitive. So let me clean up the data a little bit more. I know that there's some jitter in how the data was collected, but I know that these are all the same point in time. So now let me overlay them exactly. And now you start seeing something interesting. Okay, now you can actually see, oh, there is some site signal here. If I look at the newer runs of this vaccine, this recipe, I start to see like they close just a little bit too much here, and I start seeing this like little downward trend. So now let me add in, those were 35 like working runs. If I add in the 36th and 37th, the 37th was the known failure where the vaccine batch was scrapped. 36 actually thought it was okay, but it turns out actually you see a failure in progress there. And even more than that, you actually now have a predicted signal. You can just look at how open one of these valves is at a certain number of seconds after the recipe started. It should be the same, but actually you see this nice little linear failure graph showing you that this valve is over time opening slightly too much, more and more and more, until you get a limit, and then it finally has a catastrophic failure. And the reason why I like showing this example, one is because it's a very high value problem to solve. It's a very expensive failure when you ruin an entire batch of medicine in a factory. But also, you didn't need to really know anything about what the signal was measuring. You just needed to know that it was collected in a standardized way, that it was should be identical. You had the right context of when it was in the recipe, and it was the same recipe. And using that, you were able to define a predictive health signal that ended up being really high value for maintaining these valves. But one thing that definitely was required was expert human analysis. There was no software system that would have done that for you. It's just if you had the data and the problem was valuable to solve, you could go in and figure it out yourself. So the question is AI capable of doing this kind of analysis now? If you have this data, could you have it make you something like this? And not yet, but it's getting decently close. So it's interesting to talk about.